So let's go on to the next section. So here we're going to talk about another application of the integral, the definite integral. What we've already talked about is a couple different applications. How do you find volumes of these volumes of revolution like we were talking about? Turns out we need a definite integral to do that. Well, we're going to need that for calculating work done by a constant force, or sorry, over a variable, by a variable force. That's going to require an integral as well. So let's go on to 6.4 and see why we are going to need a definite integral for work. And of course, this is the physics definition of work. This is very specific what work means in the context of physics. And so you can see, what is work? Work is force times the distance. That's it. You have a force and you multiply it by a distance. That's what work is. Now, when you get to calculus 3, what you'll find is that this is actually, in 3 dimensions, force is actually a vector, and then the distance could also be a vector, I guess. Oh, no, yeah, I guess the distance would also be a vector. So that actually turns into what's called a dot product in calculus 3. And by the way, calculus 3, what you're going to do is basically all the stuff we're doing in calculus 1 and 2, but we're just going to extend that into the 3rd dimension. So that's what you got to look forward to in Cal 3, which I am teaching in the fall, by the way. I am teaching Cal 3, and I'm doing it in the same exact method here over the WebEx stuff. All right, so let's take this apart, the definition of work in the context of physics. In order to do this, we need to talk about, well, what is a force? Well, according to Newton's second law, force is equal to mass times acceleration. F equals ma. And if any of you are taking any physics or have taken any physics, I'm sure you've seen that before. Okay, now acceleration can actually be expressed in terms of position, right? If you remember our calculus 1, if you have a position function, then the acceleration is related to that in that the acceleration is the second derivative of the position, right? So we could actually write this as what's called a second order differential equation, if you wanted to get technical about it. So F is equal to mass, force is equal to mass times the second derivative of the position function with respect to time. That is, in fact, is right there. That is a second order differential equation in case anybody's interested in that. We will talk about more about differential equations a bit in this class. And then, of course, there's the class called differential equations where you'll see a lot more. We do get to do a bit of it in here as well. Okay, so we've already said work is equal to force times distance. If the work that's being done is constant, the units for work are foot-pounds, inch-pounds, foot-tons, any sort of measurement of distance times a measurement of force. That's where you get the units for work. And in the metric system, it's a Newton meter, but a Newton meter is actually a joule. So Newton meter is actually what's called a joule. Maybe you guys have heard that as well. Okay, so this first problem illustrates the fact that we don't always need to use calculus to find the work done. Look at the first example there. Let me clear this out of here. Example 1 says how much work is done to hoist a 200 kilogram rock to a height of 3 meters. Very simple question. In this case, work is just force times distance. We have a force there, although 200 kilograms is not really a force, that's a mass measurement. 200 kilograms is a mass. How do we get force out of a mass? There's no, if you have a mass and you want to get force, well, just look at the Newton's second law, right? Mass times acceleration. And what is the acceleration that we're all experiencing? It's the acceleration due to gravity, so 9.8 meters per second squared, yeah, g, exactly. So that those two together are going to give us the force, and then the distance that we're going, 3 meters. You can kind of look at the units. In fact, if this were a physics class, I would definitely be uh, focusing a lot more on the units. So let's see, 200 times 9.8 times 3 is 5880. So 5880. And let's at least take a look at these units here. What are these units? Kilogram meter per second squared. That's the units of force, right? Kilogram meters per second squared. And then if you multiply that by another meter, what are the units of force again? Kilogram meter per second squared is a Newton, right? And then if we multiply that by another distance unit, that becomes squared. And so that's a Newton meter. And then a Newton meter is a joule. So 5880 joules of work. Okay, so this was simple. This is just using the definition of work, force times distance. No calculus required. So why do we need to use calculus in some other circumstances? Well, also let me just ask you a conceptual question. Suppose I have like a table here. There's a table maybe that's got something on it, right? It's got a block on it. This block has some kind of mass. If I move that mass this direction, even if I just take it off the table and carry it in that direction, am I doing any work in the physics context anyway? Anybody take physics and know what the answer to that is? Take that mass and just move it directly horizontally off the table. So carrying it so that it stays the same distance from the ground all the time. Any work done? All right. Well, okay, remember, but it's distance moved against a force, right? So are we doing any, sure, perhaps. I mean, if you include friction, suppose that I picked it up a tiny bit off the table and just carried it directly horizontally. If I didn't push it against the force of the table, friction of the table, I just sort of picked it up and moved it directly horizontally. I'm not doing any work in that case because I'm not moving the mass against a force. I'm moving it, in fact, directly perpendicular to the force. If I instead take that mass and move it up, then I'm doing work because I'm doing work against a force, the force of gravity. Okay, and in fact, if I do that in any direction that has some kind of vertical component to it. So this one would be no work done because I'm not moving it against any force. This one, work is done. Okay, so anyway, just keep that in mind. You have to be moving the mass against some force. If you're not moving it against any force, you're not doing any work. Okay, so let's see. Why then do we need calculus, or in what circumstances do we need calculus to find work done? So this is work done by a variable force. That one that we were just doing is work done by a constant force. Variable force. Now, in fact, technically speaking, gravity is a variable force, but for the purposes of what we're doing, the force of gravity is pretty much constant almost everywhere on Earth, right? I think if you go to the top of Mount Everest, you might be able to, take an instrument up there and detect that the force of gravity is slightly less. But for the purposes of what we're doing here, gravity is pretty much a constant force. However, if you are talking about like doing, taking something from the surface of the Earth and putting it into orbit, well, then it definitely becomes a variable force, right? Then once you get a few hundred miles up away from the surface of the Earth, well, clearly the force of gravity is going to be a lot less way up there than it was at the surface of the Earth. So when you're talking about moving an object a very long distance vertically away from the surface of the Earth, then you do have to consider that gravity is a variable force. But for the purposes of what we are going to do here, we can look at something that does have an obviously variable force, and that's Hooke's law. And Hooke's law is springs, right? What does Hooke's law say? It's written right there. So F is equal to KD. That's what Hooke's law says. And basically all that says is that the force exerted by the spring is proportional to the distance that the spring is either compressed or stretched, right? So in other words, if you push on that spring harder, in other words, the distance of the spring becomes shorter and shorter, the more that it gets compressed, the harder it's going to push back, right? In other words, the force increases as the spring compresses more. So how do we then determine, say, the work that is done by a spring, or the work that is done to compress a spring a certain amount? How do we figure that out? Well, let's think about it. So the situation we might have is, suppose we've got a block or something, an anchor for the spring, and here's the spring, right? And then suppose I'm moving that, well, actually, let's say, maybe do this actually. I'm going to say, here's the anchor to the spring, here's the spring, and then suppose we have a block attached to the spring, right? And we're trying to figure out how much work would be required to, say, compress that spring a certain amount. So let's think about how that might work. I'm going to just put a line here and say that's where the spring is at its natural length. And suppose that I want to compress it, right? And I want to push it that much. And I want to say how much work was required to push the spring that much. Okay, how might we go about doing this? Well, what we can do is we can divide this up into a bunch of subintervals. And I'm going to just look at one of those subintervals right there. We have several of them. And then there's one of them right there. Let's call this one here x sub I. And we'll call this little width here delta x. So what we can do to kind of figure this out is we can say, well, let's suppose that the amount of force required to, or the amount of work required to push that spring just that tiny little distance, delta x, we'll assume that's constant, okay? So the work required to move the spring, or compress the spring, let's say, a distance of delta x, what would that be? Let's just assume that it's constant. So the work is the force times the distance, right? Force times distance. So it's just going to be force times the distance that it's going is just delta x. And in fact, actually, what I should say here is that this is f of x sub I times delta x. Because remember that the force that's required on this little tiny bit at where we are, at where that delta x happens to be on the x sub I, that force is going to be different than if I were to say move it over a bit, right? Like suppose the spring is more compressed, then that force would be more in that part of it. And if it was, say it was to the right, then it would be less out there. Everybody see what I'm saying? So this is like a little bit of work. We can call that like work sub I, just the amount of work required to move it that tiny bit right there. Okay? So then what would be an approximation to the total amount of work done? Well, what we could do then is say, well, what if I take all these little bits of work? So like this bit here, how much work to do that bit? How much work to do that bit, right? And as we go from, compressing it more and more, each one of these is going to have more work, right? So like this is the easiest one, right? The first little bit, easy. Then the next one's a little bit harder. Next one's a little bit harder. So it's going to require more and more work to move it as we compress it more and more and more, right? So suppose that we treat each of these little subintervals as a tiny little bit of work that we're doing, and then we just add them all up, right? So suppose if we did that, we would get the sum from I equal 1 to n of f of x, we'll use that capital F there, f of x sub I delta x. And then if I want to get the exact amount of work required, that would again just be an approximation, because again, we're assuming that each little subinterval, the amount of work is constant, but we can't really actually make that assumption because it's constantly changing, right? No matter how tiny I make those delta x's, the amount of work at the beginning of it is going to be less than the amount of work at the end of it. However, if we take the limit of that as n goes to infinity and just divide this up into like an infinite number of little intervals, that will give us the exact amount of work. And so this is what we get if we consider that. And that, again, is starting to look an awful lot like an indefinite integral, and that's in fact exactly what it is. So that is how we arrive at this formula to find the work done by a variable force. So we have to add up a whole bunch of tiny little bits of work, and that will give us the exact amount of work that's done. Okay? Any questions about that one? And you can kind of, you can just, if you want to think about this as going into orbit as well, right? Like suppose that you were talking about taking an object into orbit. Well, then you would divide up the distance traveled from the surface of the Earth up to like 500 miles or however far you want to take it, chop that up into a bunch of little subintervals and figure out how much work would be required for each subinterval and so on and so on. So this would work for a different type of force as well, not just a spring. It would work for putting an object into orbit. It would work for taking like a positively charged particle and taking another positively charged particle and pushing them towards each other, right? Because the closer they get, the more work will be required to overcome that force. So yeah, anything that has this sort of variable force associated with it, you can apply this to. So let's do an example of the spring one. Example 2. It says, a force of 30 pounds compresses a spring 5 inches from its natural length of 20 inches. So 30 pounds, 5 inches. And the fact that the natural length is 20 inches, that doesn't matter. At least in this problem, it doesn't matter. Okay, so how are we going to do this? All we have to do here is just say, well, what is the force? So in this case, pounds is actually a unit of force. And I'll talk about that in a second when we're finished with this problem here. So we don't actually need to include gravity in this. So 40 pounds, the distance 5 inches. So what we're going to do here, in fact, I don't even need to write that. We'll just say that the total amount of work done is just going to be the integral from where's the starting, let's say we're starting at position 0, that would be the natural length of the spring, compressing it 5 inches. And what I'm saying here is, like, suppose that you have the spring like this, right? In its natural state, we'll say that this block is at position 0, okay, position 0. And then what am I doing? I'm compressing it. And where I stop, that'll be at 5. Okay, that's what we're talking about. The natural length of the spring would be 20, doesn't really affect anything here. Okay, so the force here is just 30, or actually Hooke's law. So we'll have to find that, and we'll do that in a second here. That's what the integral that we're going to have to find. So using Hooke's law, we have f of x is equal to kx, and it says that it takes 30 pounds to compress it from 5 inches from its natural length. 30 pounds when x equals 5, I should say. And so how are we going to use that information to figure out what that function is? Well, all we got to do is basically just say the force is 30 pounds when x is equal to 5. See that? I'm just plugging in the given force, the given distance. That allows me then to find k. K has to just be 6 then. And so now we can say, well, the work done must be, we figured out what that f of x function actually is. And the integral itself becomes very simple. It's just 6x. And then we can find the antiderivative of that, 3x squared. And so plug in 5, 25 times 3, 75. And the work here would be inch pounds, actually, inch pounds. For part B, all you would have to do is just, for part B, now it says to compress it from 8 to 10 inches. So just 8 to 10, same integrand, same force function, same antiderivative. Now we just have different bounds here. That's going to be 3 times 100 minus 64. What is that? 100 minus 64 is, what is that? 36 times 3, is that what that is? Yeah, 36 times 3, so 108. Again, inch pounds is the units here. Right. So the question in the chat there, I thought it was asking for the amount of force required to compress it 8 inches for part A. That's, oh, oh, you're right. I'm sorry. It should have been 8, not 5. Thank you. I was reading the question wrong. Let me change the bounds on that. It should have been 8, not 5. So 64 times 3, what is that? 180 plus 18, 198. Is that what it is? 192. Yeah, thanks for pointing that out. I was reading the paper and seeing 5 there when I should have been seeing 8. 192 it should have been. And then the second one, 108. So you can see compressing it for 8 inches takes 192 inch pounds. That's 8 full inches. Then only 2 more inches. That's it. The last bit is just 8 to 10. That's like almost, well, more than half the required work to take it that full first 8 inches. So 8 inches is 192. Then 2 more inches after that is more than half the work there. Why is that? Well, of course, because the more we're compressing it, the harder it's pushing back. So it takes more work on those last 2 inches than it does on, say, the first 2 inches. Okay, any questions on this one? All right, now let me just make a uh, quick little comment about the units that we're seeing here. In the English system or the American system, however you want to refer to it, um, and this is kind of important because for whatever reason this book goes back and forth between the units. Pounds is a measure of force. In the metric system, which I don't know why this book even bothers with anything besides the metric system, it really shouldn't, but it does. So we have to make this distinction here, which really should just be sticking entirely with the metric system. But we don't for whatever reason. So in the metric system, what is the unit that sort of analogous to the pound? It's the kilogram, right? And we, as lay people, we would not make any distinction between these two things, right? However, there is a fundamental difference between them. It's a measure, not a force. What is it a measure of? Mass, exactly. And mass and force are definitely not the same thing, right? Force is actually defined to be a mass multiplied by an acceleration, right? And so, well, that maybe leads us to wonder, well, okay, what is the measure of mass then in the English system? Does anybody know? The slug. Yeah, that's right. In the English system, the slug is the measure of mass. Weird. So the if you talk about slugs and kilograms, that actually measures exactly the same thing. Yeah, so pound, right, the pound then is actually that would depend on what the force of gravity is, right? Because a force, remember, a force is a mass multiplied by an acceleration. So yes, you are correct, Toby. Um, so that means that if you are in a different, if you're under a different acceleration, then your weight, your weight in pounds would could be different, right? So suppose that you like weigh yourself on Earth and then you are an astronaut and you fly up to the moon and you weigh yourself again on the moon. Well, that your weight is going to be different, right? However, kilograms and the measure of mass just in general, that is what is called an intrinsic quality to an object. That doesn't change at all. If you measure yourself in, you say you're however many kilograms, 50 kilograms in weight or whatever, um, then that doesn't change, right? It doesn't change if you go out in space or go to the moon or whatever. That's always the same. It's the effect that gravity has on mass. The force is what our scale is actually measuring. Okay, so I hope that's not any more confusing than it needs to be, but just keep that in mind. Like, for why is this going to matter for the problems that you need to do in this section? Well, remember that F is equal to ma. We have to have the force in order to find the work, right? Force times distance is work. And so if you need the force on an object and you're given in the metric system kilograms, what do you have to do? You got to get the force from that, right? So how do you do that? You have to multiply it by gravity first, right? Now, in the English system, you don't have to multiply by gravity because force is already included in the pound system, right? Gravity's already there. In fact, what is a pound then? What would 1 pound actually be? 1 pound would actually have to be what? Let's see. In the metric system, 1 newton, right, is 1 kilogram meter per second squared, right? 1 kilogram meter per second squared, right? So it's a mass times an acceleration, right? And so 1 pound, what must have to be then what was the unit? 1 slug times meter, and instead of meter, it would be a foot per second squared. So 1 pound is actually 1 slug times 1 foot per second squared. Pretty strange, but for the purposes of what we're doing here in this class, just remember, if it's metric, you're going to have to get to the force by multiplying by gravity. If it's in the English system, if it's given to you in pounds, you don't have to multiply by gravity. You just use the pound as the measure of force. Okay? That's the easiest way to maybe decipher what it is I'm trying to tell you here. All right, so now let's try some of these other work problems. This is, what are we on here? Okay, so example 3. This type of question is a bit different than the other ones, but this is probably the most common one that you're going to get actually on the homework. So let's try to follow what we're doing here. And this one is actually a bit more difficult than the kinds that I say I'm going to ask on the test or that you're probably going to see on the homework. Although you will see probably some of these more difficult ones on the homework, but it might be good to go ahead and start with a difficult one so that you can at least see all the possibilities here about what we're going to be doing. So this is a tank that is in the shape of an inverted cone, like an ice cream cone, basically. There's mercury in this. I don't know why anybody would want to hold mercury in a tank shaped like this, but hey, this is a math class, right? Just ask weird questions sometimes. Held in the tank in the shape of an inverted cone with a radius 2 meters and height 5 meters. So radius 2 meters, label that. Height 5 meters, label that. All right, so what we want to be thinking of here, and why do we need to use calculus here? Let's try to figure that out. Also, this thing says it's not all the way full, right? It's only got 4 meters of liquid in it to throw another monkey wrench into this. So what we kind of want to think about here is it's going to require a different amount of work to say, if let me draw this actually on here. I'm going to draw a slice of this tank, or a slice of the mercury, in fact. This is the mercury in the tank. Now let's picture that little slice as having its own little bit of mass and own force being exerted onto it. And let's call that thing, say that we're slicing it so that it's got height delta y. Now consider just that slice by itself and say, where does that slice need to go? Because we're talking about work, so we have a force exerted on that slice. We've got to make that slice go a certain distance. What distance is it going to have to go? It's going to have to go to the top of the tank, right? And so think about that slice that I've drawn and say, okay, I got to lift that slice up to the top of the tank, right? So there's a force being exerted on it, and there's a distance that has to travel. Now, suppose I drew the slice in a different place. Suppose I drew it up here instead, right? If I drew it up there instead, how much work would be required? Well, it's probably a little bit heavier, but it also doesn't have to go as far. So the force is probably going to be different for those two reasons. Anyway, the point is that I have to say, well, the force being the distance that has to be traveled for each of these slices is really the main problem here, right? Each slice has to go a different distance. And so therefore the work that is required to move it from where it is to where it needs to go is going to be different in every single slice. So what we have to do here is figure out how much work is required for on a sort of representative slice, and then apply that to all of the other slices that are going to have to go, and then add up all of the works for each one of those little slices, and then that's where we're going to get the definite integral out of this. So let's start labeling a few more things. I'm going to put the x-axis at the bottom of this. So let's call this the origin, in fact, right there. And so this is at height y. The slice that I've drawn now is, if this is 0, this is y equals 0 right here. Then that slice is going to be at height y, okay? And then with that in mind, how far does that slice need to go? If I'm saying that the height is at slice y, and I need to get it up to height 5, how far does it need to go? It needs to go a distance of 5 minus y. Everybody see that? So what else might we need to know about this particular slice? Well, we probably are going to need to know what its radius is, because that's going to be important in finding its mass and thus the force being exerted on it. So unfortunately for this problem now, the slice has a variable radius, right? And so all I can really do is just call it x at this point, or something else. I could call it r if I wanted to. I'm going to call it x, though. And that radius x is a function of the height that slice is above the bottom of the cone, if that makes sense. In other words, if I go towards the bottom of that cone, the x is going to be smaller, right? And if I go towards the top of the cone, the x is going to be bigger. So therefore, x is a function of y here, okay? So let's just do this step by step. Let's first consider, again, we're going to do this all on the representative slice, okay? We're going to say that let's start out with the volume of the slice. And then everything we do to this slice is going to sort of set up the integral for us to find the total amount of work. Okay? So the volume of the slice. Well, it's a circular slice, so that means we're definitely going to have to find the area of it. So that's going to be pi. And we said that the radius was x, so pi x squared. To give it volume, it has height delta y. So pi x squared delta y. Next, we probably want to consider the mass of this slice. How much does that slice weigh? Or, I guess with mass, what is its mass? So for that, well, if you remember from your physics or chemistry or something like that, we have also a density on this, right? So what is density times volume actually gives you mass? You can check the units on that are going to verify that. So we get 13,593. That's the density times the volume. Density times volume. That gets us mass. Okay? Density times volume is mass. Then we need the force on the slice. And now, again, since this one actually is in the metric system, to get from mass to force, we have to multiply this by gravity now. So 9.8. 13,593 pi x squared delta y. Now, just real quick, if you want to go through and consider the units here, 9.8, that's meters per second squared, right? Units of the next one, kilograms, right? Oh, actually, the density is kilograms per cubic meter. Let's mark that. Let me get rid of the parentheses here. We don't need that. Times 13,593 kilograms per cubic meter, right? That's the units of the density. Pi doesn't have any units. X squared, that's x has to be a unit of meters, right? So that's meters squared. And then delta y also has meters as its unit, right? So look at the units here. Meters squared times meters, right? That's cubic meters right there, which is going to cancel with that. And then what are we left with after all of that for our units? This is dimensional analysis, by the way. Kilogram meters per second squared. Doesn't that look like a familiar unit to us? Newtons, right? Exactly. So indeed, this units match here, and we are getting newtons as we should. Okay, so finally we got to the point where we're at the force on the slice, and I'm going to go ahead and simplify that. So that gives us 133. The force on the slice is 133 to 11. That's 0.4 pi x squared delta y. Okay, now let's find. Now let's do the work on the slice. So remember, work is force times distance. So really, we have the force already. Now we just have to multiply that by distance. So I'm going to write this again. Pi x squared. And now the distance that it has to travel, as we said before, is 5 minus y. And then we still have this delta y on the end. Pretty complicated, huh? Like I said, this one's a bit harder just because you can kind of see why it might be a little bit harder than suppose we just had maybe a cylindrical tank instead that had a constant radius. If it had a constant radius, that right there would be just a number. Suppose the whole thing was just 2 meters all the way down, right? The radius was just constantly 2. Then all of those would just be constants, right? All the way down to here. And if that's just a constant, then we would pretty much be ready to do the integral. Because then that would just be with the constant squared, and just multiply it with the other constants, and we'd just do the integral. In fact, when I say integral, I guess I'm skipping a step here. The total amount of work. The total amount of work is all of those slices added up. The works for all of those slices all added up. And that is where you get the definite integral out of this. And so that gives us the integral from 0. Since the, I guess I just didn't label that. Since the mercury ends at 4 meters, the last slice that we could possibly draw would be at 4. So this is actually the integral that we have to find. And again, y, if that were a constant, this all we would do at this point is just do the integral, because that would be a constant. We could incorporate it with the other constants, integrate 5 minus y. The problem here is that we still have that x that's stuck in this integral where everything else is in terms of y. Okay, so we have to now put that x in terms of y in order to finish this problem. Okay, so we need, in other words, to realize that x is actually a function of y. And what we know about this function is that f of y is linear. Why is f of y linear? Well, it's linear because if you look up at the sides of that thing, they're straight sides, right? Straight sides. They're not curved at all. That's how we know this thing is going to be a linear function. Since it is a linear function, we know that it's going to look like this. X is equal to my plus b. That's what a linear function looks like, right? My plus b. And we further know a couple of things about this function. For example, we know what x of 0 is. In other words, we know what x is when the height is 0. What is x when the height is 0? What is x when y is 0? Look at your drawing. What is x when y is 0? You see that? If y is 0, where are we? We're at the very bottom of the cone, right? The very bottom of the cone, what's the radius of that slice? Well, isn't it 0? So should an x of 0 be 0? We also know one other thing about this. We know what is the radius when the height is, when we're at the top, right? When when y is 5. So what is x when y is 5? Up and look at the drawing, it seems to be 2, right? X of 5 is equal to 2. So this then allows us to find the slope of this linear function. M has to be equal to 2 minus 0 over 5 minus 0. And that's 2/5. And so that's telling us then that our linear function must be x is equal to 2/5 y plus 0, because x of 0 is 0. And so that's it. X is equal to 2/5 y. And you can verify that that actually gives the output values that we need to see, right? So for example, notice what happens when you plug in 0 for y here. You get 0 for x, right? Which is what we expected. Look what happens when you plug in 5 for y. Well, then the 5's cancel, you get 2, right? And so it gives the output values that we need. Now you might be thinking about that slope. It looks a little funky because it looks like I've put, what have I done? It looks like I've put the change in x over the change in y, right? But in fact, that's appropriate here because it's x equals f of y, not y equals f of x. So normally when we talk about slope, it's y equals mx plus b, right? And then m is equal to delta y over delta x. But really, in general, what is the slope of any linear function without bothering with what these, how things are labeled? In general, what is m? M is the change in the dependent variable. Well, it's just a dependent variable divided by the change in the independent variable. And so that's what we kind of have to be getting used to in this Calculus 2 class, getting away from the typical y equals mx plus b situation and being able to do this with any labeling of any variables. If we're talking about a linear function, it's always change in dependent variable over change in independent variable. And the dependent variable in this case is x. Really, the best way to do it is it's this one minus this one divided by this one minus this one. So try to remember that when we're talking about how to find these linear functions that we're looking at. Okay, now we've identified what that x is. So now we can come back to the integral and say, well, what's the total amount of work then? It has to be this number, 133,211.4 pi integral 0 to 4 x squared. But now we know what x is. X is 2/5 y squared 5 minus y dy. So we finally reached the point where we have an integral that we can actually now evaluate. So that's what we have to do next. So let's evaluate that. So we got to simplify this. We're going to write this as 4 over 25 y squared, and then 5 minus y. And let's go ahead and multiply that number by 4 over 25 and see what we get. And so that gives us 2,1,313.824. We have to be that accurate, but let's do that. And then from 0 to 4, and then we get 5y squared minus y cubed. Okay, finally we're at a place now where we can go ahead and evaluate this thing. Antiderivative, 5/3 y cubed. Antiderivative, the second one, 1/4 y to the fourth. Plug in 0, plug in 4, although really we only need to plug in 4 there. So if I plug in 4, I get 5/3 times 4 to the third power. Okay, so this is 2. Let's go ahead and multiply that. I think I forgot the pi on there also. We just put pi on there. So we get that. That's 128 over 3, by the way, in the parentheses there. We're going to get this times 128 over 3. So we get 9,093,824 pi. And the units would be joules. And let's go ahead and just multiply that by pi so that we can get an answer that doesn't have pi in it. If we do that, we get 2.8. And that's probably good enough for precision there. We don't need to go crazy on that. Joules. So about, what is that, 2.8 million or so. 8 million joules.